All right, so let me briefly run through where we finished last time and maybe give a few more comments because I think this is instructive of how things are shown. So most of the times we'll be working, everything will be, all the rings will be Noetherian. I will maybe explain where we use it. So we define cohomology in two different ways. One of them was via injective resolutions, and you'll see that most of the times we don't really need it. And even in a way, an even worse definition is via flask sheaves. So this is a bigger class of sheaves, and by definition, a sheaf of flask is if restriction to smaller open subsets is always surjective, and you think about it in a way that, well, you can lift sections to bigger open subsets. And for instance, the structure sheaf is never flask. I mean, the structure sheaf, you always have more functions on smaller neighborhoods. So these sheaves are very rare in the nature where we want to deal with them, for instance, with vector bundles. However, the good thing is that flask sheaves, they have no cohomology. This is the same as we call acyclic. So the general machinery says that cohomology can be computed via flask resolution. So you can choose a flask resolution and then take the cohomology of it. Maybe let me elaborate just briefly. So you now choose a resolution of your sheaf via, I don't know, H, where these are all flask. And then you can compute HI of your F, say sheaf of abelian groups on a topological space, as simply HI of the global sections over X applied to your flask resolution. So just term by term, you take global sections, you take the corresponding complex, take cohomology. An immediate corollary that we have is that if you have an affine scheme now, so this is what we discussed, affine schemes have no cohomology according to this definition. And why is that so? Well, what is quasi-coherent sheaf, sorry, on those. So take a quasi-coherent sheaf. This is a sheaf associated to a module. Well, we have an equivalence of categories between quasi-coherent sheaves and modules over the base ring. And here, by the way, you actually do need A to be injective because Noetherian, sorry, because we will use a very specific fact that I didn't prove and I don't want to prove. This is from, this requires a little bit of commutative algebra. Namely, if you start with an injective module, then it turns out that the associated sheaf is actually flask. So I'm not saying it's an injective sheaf of modules. I'm just simply saying that it's flask. This is different. However, we've established that we can compute cohomology using flask resolutions. So what we can do now, you can start with your module to which you associate a quasi-coherent sheaf. You take a resolution via injective modules. Then what you get a flask resolution of the corresponding sheaf, I sheafified. But now when I compute cohomology of this sheaf, by definition, it's cohomology of the complex of these global sections. Well, by construction, not by definition, by construction of global sections of any flask resolution. I chose my flask resolution here. I go back, equivalence of categories, I get just the original injective resolution of my module. And as a result, the final thing, what do I get? I get that it has no higher cohomology, only the module itself. So the fact that, maybe let me give another comment, which is quite important. So since this fact that I is flask has an important corollary. And the corollary is any quasi-coherent sheaf F on an Noetherian scheme, so let's say on a projective variety, can be embedded into a quasi-coherent flask sheaf, where this is flask. So just being flask, we know, because injective modules are flask, so you can embed this, flask and quasi-coherent. Why is that so? Well, if your scheme is Noetherian, you can cover it by finitely many open affine subsets. So in particular, it's quasi-compact. Noetherian implies quasi-compact. So take the big covering by all affine neighborhoods, choose a finite subcovering. You covered by finitely many affine opens. Then on each affine open, you can restrict your sheaf, which is quasi-coherent, so it's associated to a module. And then what you can do, you can embed it into an injective module. Now you push forward from this affine open subset, this injective module, and you check that you can embed your sheaf into the direct sum of those. So this will be, again, quasi-coherent. This is an important property. All right, another corollary from the fact that we can compute things using Flask resolutions is if you have a closed embedding and any sheaf of abelian groups, then actually cohomology on Y on the closed subset is the same as computing the same cohomology of the push forward of this sheaf. So again, why is that? Well, simply you pick a Flask resolution. You can compute cohomology using this Flask resolution, but remember that we discussed last time again that Flaskness is preserved under push forward. So what happens is I simply push forward my resolution, and it's a Flask. It becomes a Flask resolution of what? A Flask resolution of the push forward of my sheaf F. If you wish, it remains an exact sequence because on stalks, exactness can be checked on stalks, and you very well know what the stalks of the push forward are. I mean, on the corresponding closed subset, they're the same as before, and on if you're outside your closed subset, well, then it's zero. All right. So now, by the very construction again, we can compute using this new resolution the cohomology of the push forward of F, but the global sections of any sheaf on a closed subset are the same as the global sections of its push forward. So you get literally the same complex. Just by the very construction, the two complexes are literally the same. So the cohomology are the same. And finally, we discussed the big theorem by Serre, which says actually that the following are equivalent for an Noetherian scheme. So if X is Noetherian, then the following are equivalent. First, X is affine. Second, quasi-coherent sheaves have no higher cohomology. And third, it's actually enough to ask for the first cohomology. So this is important. This is only first cohomology of all coherent sheaves of ideals should vanish. So here, remark that on the top, I have quasi-coherent, again, quasi-coherent. Here you might say, oh, you have coherent. So there is some finitely generated. Quasi-coherent are just arbitrary, come from arbitrary modules, and coherent come from various types. Say over an Noetherian scheme, finitely generated. But since X is Noetherian, it means that any sheaf of ideals is automatically coherent. I mean, it's already generated, it's finitely generated, because we asked for X to be Noetherian. All right, so this is just a comment on why suddenly here we have Noetherianness. All right, well, we had another definition of cohomology, which comes from check cohomology. Again, it can be defined for an arbitrary open covering. So let me not discuss about the limits, but at least maybe today, let's prove the comparison theorem, which I think is a rather neat trick to remember. This is a trick that comes again and again in algebraic geometry, and you'll see that we only use some kind of long-exact sequences. So what does check cohomology begin with? Check cohomology begins with an open covering. You start with an open covering of a topological space. Let's index it by the set I. As usual, I introduce the notation for multiple intersections. If I have U sub indices, it means that I intersect the corresponding modules there. All right, then we build this complex. I wrote it down again. The pth term. So the pth term is given by sections over all p plus 1, and this is, remember, this is indexed from I0 to IP. So p plus 1 intersections of the elements of the covering. And here I did something which I didn't originally do last time, maybe. I don't remember. But one way is to start with well ordering your I. So if you go to your set theory class, you will remember about all these well orderings, like axiom of choice, whatever. In most applications, I will be finite. On top of that, well, there's the differential, which I wrote down again. The differential just says, okay, pick an intersection and then look at the, maybe let's write again, just to remember, the differential, say the first differential D1, let me write here, the first or D0, it goes from the product of F of ui into the product over all I less than j f of ui intersected with uj. And what does this differential do? The differential of alpha I, where alpha I is a section over ui, f of ui, it sends alpha I to the collection over all I strictly less than j, and then remember what I need to do. If I remove the first index, alpha j restricted to uij minus alpha I restricted to uij. So I drop the first index, I look at the corresponding element, I restrict. I drop the second index, I looked at the corresponding element, I restrict. And of course, from here, you see that the kernel of D0 are just sections. The sheaf condition says that these are just the global sections over X of F. This is our definition. So by the way, I probably didn't write, of course, that the check cohomology with respect to the covering P of U F is just the usual cohomology, Pth cohomology of this complex. Right? But this complex essentially depends on the covering so far. So the first comment that I briefly also made last time is that there are various versions of this complex. So one thing that we can do is we can put no ordering on these sub-indices. And for every collection of indices, I define this complex, and it becomes very, very big. So this, if I is finite, then this complex is, of course, 0 starting from P equals to the P equals to the cardinality of I. If I put no restriction here, no ordering on the tuples, then I get an infinite complex. For instance, these guys can repeat, etc., etc., etc. But it has some advantages sometimes. Another thing is that inside this complex with no ordering, I can produce alternating cochains. Alternating in what sense? Well, if I have a well ordering, I just simply request that, for instance, if two indices are the same, then it's 0. And if I have a permutation of indices in terms of the well ordering, then I put a sign, and this sign adds to, I mean, you can imagine, it's like the exterior power of a vector space or something. However, for us, it's enough to consider this general complex. So maybe, again, one last comment is that in general, and this is what I said and kind of almost explained last time, or briefly explained, you need to pass to the limit with respect to all coverings. And then this is how you get rid of the covering in the definition of check cohomology. You produce cohomology by passing to the limit, taking finer and finer coverings. But in algebraic geometry, technically, at this point we don't need it. Let me give another comment, by the way, is that as we discussed last time, a typical problem is with this definition of cohomology is that on a topological space, as long as it's, for instance, irreducible, then any constant sheaf is Flask. So if you, on a scheme, say, on the underlying topological space, you take a constant sheaf, Z, and you try to compute its cohomology, then it will have no higher cohomology, constant sheaf Z. However, you can consider on the same, say, your varieties over the complex numbers. It's over the complex numbers. What you want to do, you want to compute cohomology of the same sheaf in the analytic topology. And now in the analytic topology, what you will get is you'll get the usual Betti or Durham cohomology of your variety, which is a big problem. I mean, it's not a big problem, but you want to compare in some sense algebraic and analytic cohomology, and suddenly you have this discrepancy. So this problem was solved many years ago by Deligne, for instance, who introduced étale topology, so-called, which is not topology in the usual sense, but it's topology in the sense of Grothendieck, the so-called Grothendieck topology. And étale topology allows you to build, again, to construct cohomology in this topology, and you start having comparison theorems. What is very interesting is that, again, check cohomology, don't disrespect it or disregard it, because it very easily, again, generalizes to this more complicated situations. So you again have definitions of coverings, you can pass to limits. So what's our example computation? I looked up in Hartshorn for some examples, and then I realized that there's a very neat example of just computing cohomology of the sheaf of differentials on the projective line, which I've taught algebraic geometry many times, but I never did this computation for some reason. I will just remind you that the sheaf so what are these? These are differential forms on your projective line. But this is technically isomorphic to O of -2. We will discuss it later as the next example. So let's compute cohomology of the sheaf of differentials using the standard covering of the projective space. So what do? We cover it. You have your homogeneous coordinates. U0 is, say, where the first 0th coordinate doesn't vanish. U1 is where the second one doesn't vanish. Both of them are affine spaces, right? UI are just affine spaces. And let's say the first one has coordinate x, the second one has coordinate y. So what are those? What is our complex? Our complex has just two terms. This is the first term of our complex, and this is the second term of our complex. All right. Well, the first one will compute as global sections. The second one will compute as the first cohomology. What is the intersection? The intersection is the punctured affine line, right? U01 isomorphic to A1 without 0. And what I did is I identified the coordinate on this intersection. I embedded the intersection in U0. So I'm saying the coordinate on U0 is x, the coordinate on U1 is y. The coordinate on the intersection is x, but since the line is punctured, I have x inverse as well. What are the algebraic differential forms? Well, on the affine line, differential forms are, of course, we know there's one generating differential dx, and then you can put any polynomial coefficients. Same on the second line. And finally, I need to take the differential, which is just the restriction. But how does the restriction work? Well, let's see how the restriction works. So I continue writing. I want to take the differential of this pair. This is one section. This is the section belongs to f of U0. This belongs to f of U1. But then when we restrict, the following thing happens. Well, first of all, when we restrict, we get minus p of x dx. But then we should add plus q of y dy restricted to u naught 1. But when we restrict to u naught 1, we know that y goes to x inverse, right? I need my change of coordinates, and on the intersection, if I go from one patch to another, I just invert the coordinates in this case. All right, well, then we can continue writing. This whole thing equals minus p of x dx plus q of 1 over x. So we take a usual polynomial, but now it's in the variable d of 1 over x. And then what is dy? Well, it's d of 1 over x. All right. For those of you who did their calculus, we've done it recently, it will be easier than for me. Well, for me, it's also reasonably easy. So it becomes minus p of x minus 1 over x squared, q of 1 over x dx. All right, and now let's see what's sitting here. What can I get? What's written here is anything of the form 1x, x squared, etc. But also from the second part, from here, so this comes from I, this comes from P, and from this part, we get anything of the form x to the power minus 2, x to the power minus 3, etc. So we have the leading term x 1 over x squared, but then we multiply it by a polynomial in 1 over x, so we can get rid of any power that is lower than 2. All right. So what do we get in the co-kernel? We now need to quotient by this, and when we take the quotient, so after taking the quotient, we get a one-dimensional vector space. So we get that H check 1 over P1 over this omega. I didn't write U here, the covering, but as we'll see in a second, the covering doesn't matter in this case. H1 is isomorphic to, well, to K, to our field. Everything is over the field. And this is generated by x inverse dx. It's kind of generated by this rational form. All right, well, a more general example, as I said, you actually know that this omega is isomorphic to O of minus 2. It's a line bundle. Well, for a more general line bundle, let's just use the same covering to compute cohomology of these line bundles. So using the same covering, what do we get? We get the following complex. So we start with U naught, f of U naught plus f of U1 goes to f of U naught 1. Now, it's a line bundle where you have on the intersections, you have on the restriction an extra thing happening. So which extra thing is happening? Let's see. It's reasonably easy to check. So the sections over U1, these are just, they become free sheaves. We might think that this is K of X. This is K of Y. Direct sum. And here, again, this is free over the intersection. So we have K of X, X inverse. But now we need to look at the differential. What does the differential do? Well, we have a pair of polynomials, a section over u0, p of x, a section over u1, q of y. Where does it go? It goes to minus p of x, because p of x restricts in the same way, plus q of y restricted this section to u0, 1. I mean, the first one we also restricted, but again, I use that the punctured line, I think of it as embedded with the same coordinate as u0. But what is this restriction? Well, when you do the restriction, this is the same thing as minus p of x plus, and here you do q of 1 over x, but this is not enough because remember that O of n, the very ample line bundle, well, not necessarily very ample, sorry, the line bundle O of n, the way it's defined is that on the overlaps, you have this gluing function. And what is the gluing function? Well, the gluing function is specifically x to the power minus n. So now we can do the very same analysis that we did before. So what is happening? In particular, we can compute the check cohomology now of P1 of n directly. We can first of all compute the global sections. So global sections over P1 of O of n. This corresponds to the set of pairs P of x and Q of y, such that P of x equals x to the power, did I say minus n? Why did I say minus n? Sorry. Here we have n, of course. Such that P of x equals x to the power n, q of 1 over x. And now we see, let's look at this condition. If n is greater or equal than 0, so p is uniquely determined from q. So the only thing we need to check is those q for which the expression on the right is an actual polynomial. If n is greater or equal than 0, then any q of degree less than or equal than n gives a section, a global section. And if n is less than 0, then no such pairs. All right. Well, now let's compute the first cohomology here. The first cohomology, check first of P1 of n. Again, as before, as we've just computed, this is an exact example. Remember here, what we had is well, with the sign minus, we don't really care. With the sign minus, we had x to the power 2 here. And here we have x to the power n. So the sheaf of differentials was a particular example of such a sheaf with n equals to -1. So what do we get here? We get h1 check on P1 of O of n is isomorphic to what? It's isomorphic to the quotient of k of x inverse, quotient by the set or the subspace. Let me write the subspace instead, of things of the form x to the power n q of 1 over x minus p of x. And now you look at the monomials that you can obtain using this thing, using this procedure. So if n is greater or equal than -1, and this is important, then this quotient is 0. Why? Well, because from this polynomial P, you can get all the monomials of non-negative degree. But then if n is at most -1, then using Q of 1 over x, you will get all the monomials with negative degrees. So if, however, n is less than or equal than -2, then you start leaving out monomial, and the quotient is generated by, well, what do you not get? You don't get x to the power -1, x to the power -2, etc., up to the largest negative monomial you get is x to the power n, which is negative. So x to the power n plus 1. So in particular, the dimension of this thing equals -n -1. So remark that for n equals 2, n equals -2, we get exactly the result as before, the dimension equals 1. This was our principal example here. All right, finally, let's move to the comparison theorem. So how does the comparison theorem work? This is a pretty neat trick. We start by sheafifying the check complex. So remember the check complex, instead of, let's go upwards. So what was the check complex working with? The check complex over all ordered pairs will look at sections over the corresponding intersections. Well, let's replace sections with the actual sheaves. Well, we want sheaves on X. So what we do is for all ordered pairs, we take the sheaf, we restrict it to the corresponding open subset. And here I use everywhere. So this J is the open embedding from U I naught IP into our X. So it's just a way of producing a sheaf, again, of producing a sheaf over our, on the same space, on the space X. So what are our elements here now? We get, this is a sheaf, remember, quite big. For each P, it's a sheaf. And the important thing is, with the same differential as before, well, check how it's defined, that the maps are defined from the level of sheaves, this thing becomes a resolution of F. Let me specifically write this down. So we get a resolution 0 goes to F, goes to, well, the first one will be the product over all I, the push forward of F restricted to UI, blah, 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 and you have the differential. All right. What is happening next is remark that if F is Flask, then cohomology, check cohomology of our guy is, of our sheaf is 0 for all I greater than 0. Why is that? Well, first of all, push forwards preserve flaskness. So in particular, look at, first of all, look at the global sections of this C. So C curly, which C curly is a resolution. It's an exact sequence of sheaves. Look at this guy. I claim that this guy now, this guy, is the same as C without the fancy font, non-fancy C of U of F. So this is the check complex here, and here is the check resolution. However, push forwards preserve flaskness, and products also preserve flaskness. So if you started with F that was flask, then these restrictions are flask. Tautologically, restrictions are very easy to see that they're flask. I mean, you just, a pair of open subsets in here, the sections will be the same as on the big sheet. Now, the push forward of each of the components will be, since push forwards preserves flaskness, this will be flask as well. And now finally, the product of flask sheaves is flask. So what do you get? You get a flask resolution. So actually, this check resolution can be used on the one hand to compute cohomology as we defined originally, but also the global sections of this check resolution not only computes cohomology, but it also gives you the check complex, and the check complex computes check cohomology. So as a result, this check cohomology is 0, because if F is flask, then it coincides with cohomology defined as before. All right. A very good exercise is to construct a natural map. Natural means functorial in F. For a given covering, you always have a map from the check complex to cohomology. To be honest, this is a rather general fact that if you have any resolution, then you can, any resolution of this form, so our resolution is the fancy check resolution, then you can construct a map from it to any injective resolution. So this is one way of seeing it. So hint, construct a map from C fancy U F into some injective resolution. This is injective. And then I claim that it will give you a morphism on the corresponding things. Yes, maybe the important thing that it's natural, but it's, you can check that it's genuinely functional. All right, finally, we can prove the big thing. So what does the big thing say? It says if X is Noetherian and separated. So I remind you that the separatedness for us, the most important part is that the intersection of affines is affine. You cannot drop this condition. For everything I say, a very good, it's a very good mathematical habit to try and afterwards think of counterexamples. So the most important counterexample of non-separated things is, of course, the line with the double origin. So think about whether it works for the line with the double origin or not. If X is Noetherian, separated, and you have an affine covering, then you have an isomorphism, this natural map I here. So this map becomes an isomorphism. All right, how do we prove it? We prove it using induction. All right, let's use induction. And here we start with something that I discussed earlier. We start with the sheaf F. So induction on I, if I equals 0, then both the check complex, both check cohomology and our usual cohomology, they just simply compute global sections. So for I equals 0, there is nothing to prove. So assume I is greater than 0. The first step is, and this is what I've said, a very typical argument in any kind of cohomological computation, theorem, whatever. Instead of using any proper constructions, you prove a few things about constructions, and then you use long exact sequences. So I embed my quasi-coherent sheaf F, yes, F is quasi-coherent, of course. If you have a quasi-coherent sheaf F, I claim that I can embed it into a Flask quasi-coherent sheaf. And this is where I use that X is Noetherian. So we go back, we go back, we go back, we go back. Here, I said, since on affine schemes, we can embed things in quasi-coherent Flask, then for any quasi-coherent on an Noetherian scheme, we can also embed into something Flask and quasi-coherent. And this is what's important. So let me add to the original theorem here. So this is very important. Here, F is quasi-coherent. All right, so we embed it this way. So now let's look at the corresponding check complexes of the three sheaves. I claim that you always get here, so an exact sequence of complexes, the induced thing, check that it's exact. And here we essentially use that first, sheaves are quasi-coherent. Correspond to modules. Over affines. And second, separatedness. We use that all I naught U, I naught IP are all affine. So I said, since there are intersections of affine ones, and I started with an affine covering, these guys will be affine as well. So now I have a long exact sequence of complexes. But if I have a long exact sequence of complexes, to this long exact sequence of complexes, this is a general fact from cohomological algebra, I get long exact sequence of cohomology groups of these complexes. So what does this long exact sequence give us? This long exact sequence gives us 0, goes to gamma of x, f. This is what we're interested in. Goes to gamma of x, g, goes to gamma of x, h. And this is because we know that this is the same as cohomology of the corresponding thing. All right, so what do we get next? We get a connecting homomorphism, and this goes to H1 check of x of u, comma, f, goes to the first check cohomology with respect to the discovering of G, but G is Flask, and we've just seen that since it's Flask, here you'll get 0. Goes to H1 check of U, comma, H. Then it goes here, and we get H2 check of U, comma, F. Goes to 0. Goes to well, etc. So now this map is isomorphism, an isomorphism, because it has zeros on the sides. So what we see is we see that hi plus 1 of u f check is isomorphic to hi u check h. Now, by induction, this guy is isomorphic to hi of x h. But from the usual long exact sequence of cohomology without checks, we also know that this is isomorphic to hi+ 1 of x f. So you see, this comes from the usual long exact sequence of cohomology. All right, that's it. I mean, we just now simply induct. For instance, you get all the isomorphisms. I mean, except maybe this is important, that this H1 or H1, we simply use that the H1 is the co-kernel of the map from gamma to gamma, but again, gamma to gamma, this will be the same co-kernel as for the usual long exact sequence of cohomology, because the beginning of this sequence will be the same. So you need two things. You need, for I equals 1, you need to check that this guy, you need to remember that this guy is the same for both definitions of cohomology. And for I greater than 1, you simply get isomorphisms and you induct. That's it. So as you see, just playing with long exact sequences, there's nothing but playing with long exact sequences. So maybe let me write here a few corollaries, which are very, very, very nice and important. This. Okay, so corollaries. And this comparison theorem allows you to reprove very easily some of the things that we used higher machinery for. So first, if X is affine, then quasi-coherent sheaves have no higher cohomology. Indeed, proof take the covering with simply one element. I mean, if you have a covering with one element, all the terms of the check complex, the higher terms, will be simply 0. Here is another nice thing, second one. If X is if X is projective of dimension D, then HI of XF, where F is quasi-coherent, equals 0 for I greater than D. In other words, this is a corollary of the Grothendieck's theorem. So we discussed Grothendieck's theorem, which says that on an Arthurian topological space of dimension D, all higher cohomology in degrees greater than the dimension vanish. But it's a stronger theorem. But in algebraic geometry, you can deduce it from the check complex. And indeed, so what we need to do, we need to find, or it's enough to find, an affine covering what kind of affine covering? An affine covering with at most D+1 terms. How do you do this? Well, how do you find any affine open subset on a projective variety? Well, let's embed X into Pn, where n is big enough. Since it's projective, it can be embedded in a projective space. And now take D+1 generic hyperplanes. H1, H0, HD. Then what do we know? We know that the intersection with each hyperplane further and further will reduce the dimension. If it's generic, it will reduce the dimension of your variety. So if we pick those generically, then X intersected with H naught intersected, etc., intersected with HD is empty, the empty set. But then put V to be the complement in Pn of Vi to be the complement of Hi. This is in a fine open subset. I mean, this a complement to a hyperplane in the projective space is affine. And put Ui to be the intersection of Vi intersected with X. So this is then X is covered by U naught up to UD, where all Ui are affine. So this is a typical covering. And maybe a very good exercise here. Well, where do I put it? Well, compute. Well, let me give it later. It's not that important. Or actually, let me move this and give you an exercise, because it is important. So let me move this here. So exercise. Let X be the set, the vanishing set of P of X, Y, Z equals 0 inside P2, where the degree, so the vanishing set of a homogeneous polynomial of degree D. I mean, this is not the dimension anymore, this is the degree. Use the previous method. To show that H1, well, let me introduce this notation that I will use anyways. So Hi of XF will be the dimension over K of Hi XF. This is the first notation. Well, this is the notation. Show that H naught of the structure sheaf of X is 1. And show that the dimension of the first cohomology of the structure sheaf is actually 1 over 2 d minus 1 d minus 2. Okay, so in other words, as we'll see, this number is called the genus, which corresponds to the genus of the corresponding complex curve. I mean, it's or Riemann surface. So after all, over the field of complex numbers, what we're dealing with a projective curve, which corresponds to a Riemann surface, algebraic. And then it has a certain number of holes and it can be glued out of tori. So it's a surface with a certain number of holes, which is usually called G. And you will see that this is particular H1 of O of X, and a degree D plane curve is of genus 1/2 over d minus 1/2 of d minus 1 times d minus 2. So d equals 1 corresponds to a single line. Of course, a single line is just a sphere topologically. D equals 2 is a conic, but a conic is actually also, it's isomorphic to a projective line. And starting from d equals 3, you will get first the torus, which is the a typical example of an elliptic curve. All right, so we switch to projective varieties and specifically why we can write the dimension here over the field. So this is a theorem of Serre, which I mentioned last time, and maybe it's worth discussing. The theorem of Serre says specifically that if X is a, I should stop erasing things. If X is a projective variety, and here maybe let me give a comment. So more generally, if it's Noetherian projective over a Noetherian base spec A, this will be important when we discuss push forwards, higher direct images, and O1 is a very ample line bundle. Then what we have is we have that first, all of the HI are finite dimensional vector spaces. The corresponding comment here is finitely generated A modules. And also, if you fix a quasi-coherent sheaf, so again, all the sheaves from now on, all our sheaves are quasi-coherent. Sorry, this time coherent, not just quasi-coherent or coherent. So finitely generated, very close to, for instance, vector, locally free sheaves associated to vector bundles. This is our most important thing. Then if I twist F by a big enough power, so I remember the notation, I recall the notation F of n is F tensor over OX by O of n, where it's a big enough power of the very ample line bundle. Then a big enough twist has no higher cohomology. All right, well, how do we prove it? Well, the most important thing probably is here. So this comes from Serre's theorem, which identifies, well, which gives an equivalence between quasi-coherent sheaves, and, well, let's say coherent, where from now on everything will be coherent. Between coherent sheaves and the category graded modules modulo finite modules. I suggest, well, you were supposed to know the construction, but if you do not, please look it up in the original Serre's paper or any algebraic geometry textbook. Basically says that, again, as in the affine case, you can associate the module, blah, blah, but modula some finite data. So finite data is you can destroy your module, you can tweak your module up to a certain degree, up to a certain grading, but if two modules are isomorphic in higher degrees, then the corresponding sheaves bundles, they will be the same. But as a corollary from this, we get that any coherent sheaf is a quotient of a direct sum of finitely many sheaves of the form of Ti, where these are simply twists. So these correspond to generators of the corresponding module. All right, and now all you need to do is we will do descending induction of the number of cohomology. So we now write down the long exact sequence of cohomology. And what does the long exact sequence of cohomology says? Well, it says that H P of X comma F is isomorphic to HP plus 1 of X comma G. Why is that? Well, what is happening? I wanted to move this. So this is our part. So this is the connecting homomorphism. Here we have HP of X, and here we have this direct sum O of TI. And here, well, all right, there's a little bit, should be a little bit careful. So let's first, the first thing that we do is we look at everything. So I forgot to say something. So we do on Pn. So we embed into our projective space on Pn, since we have an isomorphism of Hi on X of F is isomorphic to Hi P n J star of F. So we discussed that under closed embeddings, cohomology we can embed. And now we do everything on the projector space. So now we may assume that X equals Pn. And now afterwards, in the long exact sequence, here we have HP plus 1 of X direct sum of Ti. So we wrote down this sequence, and this equals 0, and this equals 0 for 0 less than P less than N. And indeed, last time, why is that so? So last time we discussed that there's the following thing. If Pn equals the projectivization of the symmetric algebra of V star, in other words, it's the projectivization of the space V, then H, the whole cohomology, is concentrated only in one degree, Hi of P of V, Pn, of O of T, equals, and here's our computation for P1. This is what I did for specifically for P1. It's ST V star, just polynomials of degree T in the corresponding variables, homogeneous, if I equals 0, and if T is greater or equal than 0. It is S minus T minus 1 V if I equals N, the dimension, and T is less than or equal than minus N, let's see, minus N minus 1. And this is not t minus 1. This is minus 1 minus n. This, yes. And finally, it's 0 if I is not 0 or n, or minus n less than or equal than t less than or equal than minus 1. So there's this very important, very, very important whole range of line bundles on the projective space where this thing vanishes. Remember that for these twists, you have absolutely no cohomology. And this will be very, very important for us next time when I explain a certain things about, I will say a few words about derived categories and why or how this works. All right. So finally, what we need now is that this is also a computation by Serre, is that of those bundles, you get cohomology either in the topmost degree, it cannot be bigger than the dimension of your projective space, or global sections. But this specifically means, that, well, p plus 1 here is a bit too much, maybe like this. This specifically means that these two guys will always vanish. So this will be 0 for this range of p, and also the rightmost term will be 0 for this range of p. All right, so this does part of the induction. And finally, I let you deal. So finish the proof by considering the base case, which is p equals the dimension. Well, and the lowest case. So you won't anymore have this equal to 0, or you won't anymore have this equal to 0. For instance, if p equals 0, then you will get simply global sections, but you can still argue about stuff, which is very good. You can still argue about stuff. What does this show? This is a way of showing the first statement, that they're finite dimensional vector spaces, because now inductively, this is a finite dimensional vector space, thus this is a finite dimensional vector space. And remember, we're doing descending induction on p. So we start with p big, very big, and for instance, if p is greater than the dimension, then this space is 0 again, which is important. All right, this is the first thing. But now also, how do you prove the second thing? Well, you might guess that to prove the second thing, when you twist f by n big enough, all of these guys, when you twist it by n big enough, all of the twists here appearing in this direct sum will become very, very positive. And if they become very, very positive, then all higher cohomology here will vanish. Because of our computation, you see, if t is greater or equal than 0, then it has absolutely no higher cohomology. It has only global sections. And in particular, you will use induction again, and the fact that these guys have absolutely no higher cohomology to find such a twist to kill all cohomology in all degrees. All right. Again, it will be a sort of descending induction. Why is, so let me say, maybe, how much time do we have? Well, let's continue for another 15 to 20 minutes. I mean, 2 hours is a bit too much, but an hour and a half is perfect. So why a certain corollary / why are we so happy with this finitely generated over a base? Well, let's go a little bit further. And one of the most, so here's a very powerful tool. Used to compute cohomology. A surprisingly powerful tool is, instead of computing cohomology, let's sheafify cohomology. Let's put it into a relative setting. And this is something new which we haven't discussed. These are higher derived images. So we begin with a morphism of, say, even topological spaces, but we'll be interested in morphisms of varieties. So let's say you have a morphism of topological spaces from X to Y. Then, of course, you have the corresponding functor, F lower star, which goes from, well, let's call it this way, the category of abelian sheaves on X, sheaves of abelian groups, to the category of sheaves of abelian groups of Y. And I remind you that if you have an element here, F, then it goes to the following sheaf. The sections on the open subset U are the sections of F over F inverse of U. Let me rewrite it in the following form. To an open subset U, which is an open subset in Y, we associate, I will stupidly rewrite it again, F of F inverse of U, which is global sections over F inverse of U of, well, the sheaf F. Well, restricted to the subset, of course, but I mean, this is global. So why don't we replace gamma with H naught? And then here is one way to define higher push forwards. So one way to define is the following one. Definition, not great, but works. Not great, I mean not very conceptual. The ith higher push forward of F is the sheafification of the pre-sheaf, which to every open subset U on Y associates ith cohomology over the full preimage of U of the sheaf F. All right. So this is one way of defining these higher derived images, which, well, okay, this is already something. In theory, you should think about it, that we will discuss this later, we'll discuss it next time, but as a construction, you should think that it collects cohomology of F on the fibers of the map F from X to Y. This should be made precise in some way. Sometimes it works, sometimes it's not. We'll discuss it next time. One of the main applications of this machinery is so-called Zariski main theorem. but this is good enough for us for now. What is an unexpected corollary why people so excited about this, why higher derived images, is once again, it simply, very simply helps compute, strangely enough, helps compute cohomology. And just a recollection that you start with, say, sheaves of abelian groups on X, then you have the direct image functor to sheaves of abelian groups of Y, and here you have global sections on Y, which sends you simply to abelian groups. But what happens if we take the global sections over Y of F lower star of F? Well, by definition, this is the same as F of F inverse of Y, which is F of X, which is the global sections on X of F. What I'm saying here is that the composition of the push forward and the global section functor on Y is the same as the global section on X. It turns out that, so let me write it this way, gamma X, which is a left exact functor, equals the composition of F lower star, which is a left exact functor. So these are all left exact functors. For this, there is a specific machinery done by Grothendieck in the classical sense, and this is what we'll partially talk about in the final lecture, and I will reformulate all of it in terms of derived categories, is that to such a thing, you can associate a spectral sequence of the composition. So the derived functor of the composition, the derived functor of the composition here, we have cohomology of sheaves on X. Derived functors here, you have cohomology of sheaves of Y. And finally, you can guess that derived functors here, as I defined here, are sheavifications of the pre-sheaves, the way I explicitly defined it in here. So what we get, and this guy can be computed as well. We'll discuss its properties and stuff. But the most important thing to remember is that you get a spectral sequence of the following form. Its second page EPQ 2 will be specifically the piece cohomology on Y of the Qth higher push forward of F. So this is the second page already. Starting from it, the differentials, if you've ever dealt with cohomology, with spectral sequences, you'll know that the second page is more or less where you can where you can still compute something, but starting from page 3, it gets pretty horrendous. And this converges the spectral sequence to H, P plus Q on X, comma, F. Yes. Okay. All right. Let me probably give you a very, very nice exercise. So here is a Very nice exercise. Very. Show Grothendieck's theorem, which states that any locally free sheaf vector bundle on P1 over field is isomorphic to a direct sum of sheaves of line bundles, which means that it splits. And if you want to show this, then in particular, you necessarily will want to use something else, which is very, very important. And something else is specifically, let me specifically say that cohomology is a particular case of X groups. So over a ring X I between two modules M and M are right-derived functors of what? Of the Hom thing, of Hom. So it can be computed using a projective resolution for M or an injective resolution for N. So in the category of sheaves, we do not usually get nice results. So, I mean, we have problems. We have genuine problems, but with projective resolutions. But we do have injective resolutions. And so in the category, say, if you have an Ethereum scheme and you have quasi-coherent sheaves, they form an abelian category, and you have injective objects here, and you can define X as usual. You have the Hom functor. So consider quasi-coherent sheaves on X and define X I M N as derived functors of Hom. Well, in where? Again, this is now you have to use a lot of machinery that I probably don't want or need to explain. My idea is to give you a feeling and things to remember. So in general, you should think about sheaves of modules over the structure sheaf again. And then you can take an injective resolution of N of your sheaf. By the way, let me rename these guys of F, G. However, the only things that you need to remember are the following important ones. So most important are the properties. And the properties are quite simple. So first, X0 from F to G is just the usual sheaf hom for OX modules between F and G. Second, the second thing to remember is that X1 from F to G, as usual in algebra happens, this parameterizes isomorphism classes of extensions. Isomorphism classes of what extensions? Of extensions of the form G, H, F. Just the same as in the usual, this is a very general thing from homological algebra. Third, you have long exact sequences. And it turns out that you have long exact sequences in both arguments. Just as for hom. So if you have 0 goes to G prime goes to G goes to G double prime goes to 0, then you have 0 goes to hom F of G prime goes to hom F G goes to hom F G double prime, connecting homomorphism X1 from F to G prime, X1 from F to G, etc. And same for, well, same up to reversing arrows for a short exact sequence. 0 goes to F prime, goes to F, goes to F double prime, goes to 0. Fourth, X I from O of X into any G is the same as the ith cohomology of X with respect to G. And this is no surprise because, again, this is the derived functor of homing from O of X, but indeed, remember that hom from O of X into G as a functor, this is just the same as global sections of G. So there is no surprise because the two compute kind of the derived of the same functor if you fix the first argument as O of X. And finally, the fifth one is that, well, X I from E to F is isomorphic to X I from OX E dual tensor F, which is the same as from before HI of E of X comma E dual tensor F if E is locally free, where E dual is the dual locally free sheaf bundle. All right, why am I saying this? Because actually, the last time I formulated that for smooth projective variety X, there are isomorphisms. So of dimension D, there are isomorphisms between hi of xe. This will be isomorphic where E is a locally free sheaf to the dual space of h d minus I x e dual, where D is the dimension of X and E locally free sheaf bundle. Oh, sorry. What am I writing? Tensor omega of X. So E check is the dual, and omega X is the determinant, the high wedge power of the sheaf of the differential form. So this is the same as the sheaf of differential D forms on X algebraic. So this is what's called Serre duality. However, Serre duality can be reformulated now in a much nicer generality. So in a much nicer generality, we can say actually the following, that instead of doing this dual, remark that what we can rewrite, look at the top part as xi between OX, E. It says that it's isomorphic to, here is the dual, by the way, to X D minus I between OX E check tensor omega X dual. But this we can rewrite through our properties as before, is X D minus I E comma omega X dual. So a generalization that I suggest for today well, for simplicity, let's say EF are both locally free. Then there are functorial isomorphisms. Well, actually, there's a certain pairing, and the pairing will go this way. Well, it's let me write without the pairing first. Well, today I will write without the pairing. Xi between E and F. So now I introduced another player. It's between E and F. Or to be consistent with the previous notation, let me write xi between F and E is isomorphic to the dual of X D minus I. And now I interchange E and F, but I twist F by omega. This is the dual space. So in particular, very often I can deduce various results about, say, X1, all possible extensions of two sheaves. And let me remind you that one of the properties that I listed is that X1 parameterizes such exact sequences. And for instance, sometimes if I want to compute, say, extensions between two sheaves, I can reduce it, for instance, in dimension, and this is important, in dimension 1, it gets reduced to computing simply Homs, because this will be D minus 1, or sometimes you get some vanishing results, etc., etc., etc. All right, so maybe, yes, it's already 40 minutes, 20 to 7. Let's do this time. Let's do this thing. So our plan for next time for the last time is first, I will still sketch some explicit computations. And as promised, applications, say for curves, surfaces, maybe some moduli of vector bundles, etc., etc. The second thing that I will do is I will discuss Zariski main theorem. And its guys, because this is in a way where finally algebraic geometry is shown in its fullness in this language, because it's something that you can really not prove without this machinery, at least without redoing it. And finally, I will spend, I hope to do the first two in the first hour, and the third one is I will talk about how to pack everything into derived categories. Because up to a point, derived categories are simply a way of packing all this information into one black box. But also, if we have time, I will explain how this black box can be not so mysterious, and actually how we can deduce some results about this guy. So in the meanwhile, before Thursday, I strongly suggest that you do two exercises. And the two exercises are try to show this Grothendieck's theorem. I will use it probably as an example next time, but before you do, try to prove it yourself this way. And definitely computing the genus of a degree D curve. I mean, once and for all, please do this exercise yourself, because this is very, very instructive to do it by hand. I mean, if you do it by hand once, you will be very comfortable with a lot of cohomological computations when you need to compute something reasonable. Are there any questions?